Welcome to my channel. In previous video, we'll learn about Werner's theory. So in this video, we'll see how valency bond theory applies to coordination chemistry and how metals bond with ligands to form stable complexes. So before knowing the valency bond theory, we must know the coordination covalent bond. So in covalent bond, two atoms share pair of electrons. These pair of electrons shared between two atoms in covalent bond. But in coordination covalent bond, only one atom share pair of electrons. These pair of electrons shared between two atoms. This is called coordination covalent bond. So based on this coordination covalent bond, valency bond theory developed by Linus Pauling. So in this valence bond theory, central metal ion provides empty orbital like sp(d) and ligands donate electron pairs. So the central metal ion uses hybrid orbitals to accept electron pairs from ligand, and this overlap creates covalent bonds. So valency bond theory was the first theory which explains the geometry and magnetic property of many coordination compounds. The geometry of a complex depends on the types of hybridization. See here, octahedral complexes, they show two types of complexes, that is inner orbital complex and outer orbital complex. So these two complexes are found based on which type of orbitals are participating in the complex formation. In inner orbital complex, n-1 into d orbitals are participating. In outer orbital, nd orbitals are participating, but the coordination number is 6. Inner orbital shows d2 sp3 hybridization, outer orbital shows sp3 d2 hybridization. So in inner orbitals, strong ligands are participating and they have low spin. Outer orbitals, weak ligands are participating, they have high spin. Because of strong ligands, these electrons are paired up and they show diamagnetic nature. In weak field ligands are participating in the outer orbital complexes. So most of the complexes have unpaired electrons and are paramagnetic. See the example of these two complexes. Now we'll see how to identify the hybridization and magnetic property of a complex. See the example of octahedral complex, that is hexaamine cobalt. Here first you need to identify the metal ion which is cobalt, and its atomic number is 27. Then write the electronic configuration of cobalt, that is 3d7 4s2 4p0. Then after write the oxidation state. Cobalt oxidation state is +3, means it loses 3 electrons. Then again write the electronic configuration, that is 3d6 4s0 4p. Here remember that if the strong field ligands are participating in the complex, then the electrons are paired up. So here amine is the strong field ligand, then the electrons are paired up. They accommodate 3 orbitals and remaining 6 orbitals are vacant. These 6 orbitals are occupied by 6 amines lone pair of electrons and they form a d2 sp3 hybridization. If the electrons first enter into d orbitals, then the hybridization is d2 sp3 hybridization. If the electrons first entering into s orbital, then the hybridization is sp3 d2 hybridization. So this is most important. So the coordination number 4 in transition metal complexes primarily involves two types of hybridization based on valency bond theory. Here the first one is sp3 hybridization. It shows tetrahedral geometry, and the second one is dsp2 hybridization. It shows square planar geometry. So the tetrahedral complexes, they have weak field ligands and high spin, and in square planar complexes have strong ligands and low spin. See the example of these two complexes. So this is the most important question for all type of entrance exams and theory also. Why tetracyanonickel possess a tetrahedral geometry whereas tetrachloronickel possess a square planar geometry? First, you need to identify the strong field ligand and weak field ligand. Here cyano is a strong field ligand and chlorine is a weak field ligand. If strong field ligand are present in a complex, then electrons are forced to pair up. In chloro, it is a weak field ligand, so the electronic configuration, there is no change in the electronic configuration. And next thing is, you need to know the oxidation state of the metal. Here the nickel oxidation state is +2. So it loses 2 electrons, and in strong field ligands the electrons are paired up because of there is only one d orbital is vacant. So the electrons are entering into the first d orbital, then sp2. Because of that reason it shows dsp2 hybridization and square planar geometry and diamagnetic. In tetrachloronickel the electrons are, there is no change in the electronic configuration, so electrons first entering into the s orbital then p orbital. So the geometry is tetrahedral geometry and it shows paramagnetic nature. Now tell me why tetracarbonyl nickel possess tetrahedral geometry whereas tetracyanonickel possess square planar geometry. So here first we need to identify the ligands. In both complexes they have strong field ligands, and second thing is identify the oxidation state of the nickel. In tetracarbonyl nickel oxidation state is nickel oxidation state is 0, and the second complex nickel oxidation state is +2. So here the first complex the electrons are forced to pair up. So the s orbitals electrons are forced to pair up into the 3 d orbitals. Then s orbital is vacant. So first the electrons are entering into the s orbital then p orbital. So they show sp3 hybridization and tetrahedral geometry diamagnetic nature. In tetracyanonickel, we already know that the electron oxidation state is +2 means it loses 2 electrons. So electrons are paired in the d orbital, only one vacant orbital present in the d orbital. So first the electrons are entering into the d orbital, then sp. Because of that reason it shows dsp2 hybridization and square planar geometry and also diamagnetic nature. So like this limitations of valency bond theory, it predicts the geometry and magnetic property of a complex, but it cannot explain colors or electronic spectra. So because of that reason it is replaced by crystal field theory for deeper insights. Now we'll solve these problems. First question, which hybridization correspond to an octahedral geometry in coordination complexes? We already know that there are two types of hybridizations, that is D2sp3 and sp3d2 hybridization. And second question is, why is tetracyanonickel diamagnetic while tetrachloronickel is paramagnetic? Tell me. Because cyano causes pairing of electrons. Third question, which bond results from sideways overlap of p orbital? That is pi bond. Next, what is the geometry of hexaamine cobalt according to VBT? Octahedral geometry. Next question is, which limitation of VBT led to the development of crystal field theory? VBT theory cannot explain color and spectra of the complex. That is the drawback of this theory.